Good afternoon, sir. It is with great pleasure that I am welcoming you today in order to discuss one of the most fundamental algorithms used in computer science by this day. What is greedy strategy? Well, the name itself is actually quite misleading, as greedy algorithm is not necessarily an algorithm in and of itself, but rather it's a technique implemented and used by computer scientists in order to look for the most optimal decision taken at that moment in time. This rudimentary technique can actually be quite successful in most real-life cases and applications, but that does not mean it is the most optimal solution throughout the entire process. On to the properties of greedy algorithms. Greedy algorithm can be successfully applied if it meets one of the two fundamental requirements. Firstly, it must demonstrate a greedy choice property. This means that a global optimal solution is still achievable through choosing the optimal choices at each step of the process. Greedy algorithms can also be identified if it possesses an optimal substructure. This can be identified when the global optimal solution contains the optimal sub-solutions to smaller problems by way of iteration. Essentially speaking, an algorithm can be classified as greedy when you break down a problem to each step of its process. Then, you choose the most beneficial action for its time. This will coincidentally accumulate and add up to provide a solution for the entire problem. As you can see here, this is an example of greedy algorithms. This algorithm shows a tree graph, and its greedy choice is to choose the largest numbers within the two nodes. As you can see, greedy algorithm will choose from 7 till 12 till 6 and then till 9. As the algorithm states, at that current step of each process, it chooses the highest number. But the most fundamental flaw of greedy algorithm is that it only makes the choice based on one step at a time. As you can see, this node actually has 99, which is the result of the highest possible outcome. But because at the beginning it chooses 12 rather than 3, 99 will always guaranteed to be avoided. Therefore, while greedy algorithm is an efficient solution, it is probably not the most optimal solution. A famous theoretical application of greedy algorithms is known as Dijkstra's algorithm. Dijkstra's algorithm utilizes greedy strategy. We know this because it implements optimization substructure. Say if you're trying to find the shortest path A to C, it could have the shortest subpaths A, B, and B, C, which means that it must be part of the shortest path from AC. Therefore, we could say the optimal answers from the subproblems will contribute to the optimal answer global solution. Today, we will focus on two problems in particular. Each of these problems Today we will Today we will focus on two problems in particular. Each of these problems will demonstrate and utilize the greedy algorithms in some form. We can then proceed to analyze their efficiency as well as their downsides. Let's move on to the first problem, which is known as the activity selection problem. Its main goal is to find mutually compatible tasks given to maximize the overall solution. A basic algorithm of the activity selection problem is as follows. Consider the scenario that you are given an n number of activities. Each activity will have a start time and finish time respectively. Each activity will also have a numerical variable associated in order to signify their value. This is used for the algorithm to determine and prioritize which activity will be the most optimal solution. As such, our greedy choice property is established. Thirdly, it will sort each activity by their earliest finish times. And then it will print the first activity according to the sorted times. For each activity and iteration thereafter, if the start time is greater than or equal to the finish time of the previous activity, then you would select and print said activity. Else, you would move on to the next activity. You would repeat step 5 until all activities has been processed through and accounted for. As you can see, this demonstrates an optimal substructure because it identifies the global optimal solution and it contains the optimal subsolutions to smaller problems by way of iteration, which is what step 5 does. If you were to visualize this in a graph where activity is plotted against time, you can see each activity progressing as time progresses. And you could also see that some of the activities will overlap with one another. For example, activity 2 overlaps with activity 3. Let's demonstrate the activity selection problem with a visualized example. As you can see, I've created a table with its activity, start time, finish time, and payment as mentioned in the previous algorithm. Each activity will have a start time and finish time. Each activity will also have a numerical variable associated to signify their value, and we will sort each activity by their earliest finish times, which I have done so below. Now that the table has been sorted in accordance with their earliest finish times, we can proceed to the next part of the algorithm. First, we print the first activity. As you can see, this would be A2. And for each activity iteration thereafter, if the start time is greater than or equal to the previous activity, we select and print this activity, else we move on. So by iterating step 5 for each activity, we can see the output of the result comes to A2, A3, A5, and then A6. This can be demonstrated if we were to graph it. While A4 and A1 have considerably longer timelines, A2, A3, A5, and A6 are the closest to becoming concurrent with one another, and therefore are mutually compatible. This means that you can maximize the productivity of your tasks by doing as much activities as possible. Now, there are some caveats to this algorithm. Ultimately, the goal of our program is to find a set of activities of non-conflicting tasks, which means mutually compatible, that can be executed with a given time. This means that there will be cases where it might not be possible to complete all activities shown, since their timings can collapse with one another. To prove this example, you can see that A4 collapses with A2 and A3, which means that A2 and A3 will not be executed if we were to choose A4. We can therefore finalize our algorithm by having an analysis of its time complexity and its real-world applications. Now, the time complexity is, given a set of activities where all of them are already sorted to their finishing time, the algorithm will therefore not have to sort anything. As such, the best case time complexity will be O(n). Otherwise, the average scenario will be given when each of the activity will have to be sorted and compared with one another. This will give us a time complexity of O(n log n). Onto the real-world applications. For example, a lawyering firm might have multiple conflicting consultations in the same conference room. They need to find out the maximum amount of consultations possible in order to maximize their profits. Or, the second example is, if you are a manufacturing company that have scheduled to manufacture multiple products on the same machine, such that each product has different producing times. To find out the maximum of products that can be manufactured in order to maximize their profits, you would use the activity selection problem. Now that we have analyzed the activity selection problem, we can move on to the second problem, which is known as the knapsack problem. The goal of the knapsack problem is to gather a set of S items such that the sum of the values of S items is maximized in relative ratio with the maximum weight given. There are actually two ways to solve the knapsack problem, but for now we will focus on what's known as the fractional method. Consider a scenario where you might want to maximize a profit within a weight limit. Step number 1 is, each item will have a weight and weight value assigned to it. This value will have a numerical variable in order to signify their prioritization in order to find the most optimal solution. As such, the greedy choice property is stated. The third step is to calculate the value ratio. This can be calculated using value divided by weight. You would repeat step 3 for each of the items. Fourth, you sort the items in terms of their value ratio from highest to lowest. And for each item thereafter, we iterate. Firstly, we take the item with the highest value ratio in its entirety and add its value to your profits. Afterwards, you would move on to the next item once you have completed. The fractional method comes at a distinct advantage as compared to the 0-1 method. This is because you are able to fully maximize and utilize your backpack to get as much value items as possible. So say you have an item that might not fit entirely in your backpack. The fractional method fixes this problem because it calculates the weights, the leftover weight, and it uses that leftover weight multiplied by its value ratio to break down the item in its proportional value and then maximizing your capacity load with the item itself. You would repeat step 5 until the weight limit has been achieved and you cannot physically carry more. An optimal substructure has been identified because a global optimal solution contains the optimal subsolutions to smaller problems by way of iteration. Just like the activity selection problem, it's better if we consider a visualized example. Firstly, consider our 3 items shown right here. We have established that each item will have a weight and value assigned to it. This value will be a numerical variable in order to signify their prioritization in order to find the most optimal solution. Thirdly, we calculate the value ratio of each item. You could see that item 1 is $6 per kilogram, item 2 is $5 per kilogram, and item 3, we would then to proceed to sort the items in terms of their value ratio from highest to lowest. Coincidentally, this is from item 1 to item 2 and then to item 3, from highest to lowest. For each item and thereafter, we would begin our iteration. Firstly, you take the item with the highest value ratio in its entirety and add its value to your profits. Then you calculate the weight minus the item's weight, and you do profit plus the item's profit. You move on until you've come across the fractional problem. This is where the fractional method becomes useful to us. For the third iteration, we take item 3, but such that we only take 2/3 of its weight. So it'll be 20 minus 30 minus 20, that's 2/3. It will net us 0 kilograms. That means we have used our capacity to its maximum efficiency. And our profit would therefore be 20 multiplied by 4 plus 160. Because 4 is its value ratio and 20 is what we're able to carry. When we add that to our overall profit of $160, this would net us $240, providing the most maximum value possible. Let's begin to analyze the time complexity and real-world application of the knapsack problem. Our time complexity is O(n) log n. This is because the average scenario of n items in weight S will be when the items are in no particular order, thus they have to be compared with one another. Alternatively, there could be a scenario, like our visual example, whereby each item is already sorted in terms of value ratio. This is what's called as a circular list. Therefore, the removal is O(1), and as such, the best possible time complexity will be O(n). There are several real-world applications that could be applied here. Firstly, it would be home energy management. Say your home has a certain wattage limit, in which certain appliances draw out a certain amount of power. Knapsack could solve this issue by choosing/monitoring the appliances that draw out the most amount of power in order to maximize your utilization of said appliances. Second is resource management and software. As you may know, your computer utilizes RAM in order to handle and manage the efficiency of processes that happens in a computer. Knapsack could therefore help by maximizing the processes you are currently utilizing at that current time, thus ensuring that your computer is at peak performance and efficient at all times. Now, let's move on to the next one. What's this? I'm getting a phone call. I wonder who it is. Hello? Hello? Who is this? You're disturbing my presentation.
Hello. I am Jimmy McGill and I am the lead partner in a lawyering firm. I am losing potential clients due to mismanagement and scheduling. I need an algorithm to find the most efficient way to meet most of my clients in a given day in order to maximize my productivity and minimize financial loss.
I see, I see. Well, that's a coincidence, don't you think? I'll get onto it right away, sir. Huh, another phone call. What is it now? Hello, who is this?
What's up, chiddy chiddy bang bang? It is I, Elon Musk, CEO of Tesla Cars. I want you to make an algorithm for my new Tesla Roadster models to run at peak efficiency by maximizing the utilization of car components from a fixed battery wattage. Rizky, you are the best coder I know. Are you up to the challenge?
Am I up to the challenge, you say? Well, let me prove you right, Mr. Musk.
Time to hack.
Alright, so now that the code has been developed, I guess I should explain some things. First of all, I decided to create functions for each of the programs because since we're doing two programs, I figure it's much more easier to organize them and to call out to them by having void functions. Secondly, I made structures for each of the items associated with the knapsack and activity scheduler problem. So the structure for activity scheduler, as seen, is the start times, finish times, the payment, and the numbers, and the structure and the structure for knapsack is the weight, profit, and value. Value being the value ratio. Then, moving forward, the actual main part of the program, I decided to create a sort of pseudo selection screen for the user. So it would output my name, nim, as well as the title. Then it would ask the user to basically basically input which part of the program they would like to run. So if they would like to run the activity scheduler problem, they'd press 1, and then the knapsack problem press 2, vice versa. And if the user has select, this is just a simple error. If they made a wrong value, it'll just exit the program. As well as this is a mini. I've implemented this just so the user can go back to the main menu. So say that they finished the activity scheduler, they'd want to go back to knapsack. They could just press yes, and then it'll take them back to the loading screen, basically. So on to the first one, which is the activity scheduler program. This calls the function. First of all, it sets the number of activities. This is the task. So this allows the user to basically input their custom amount of tasks. So for the example given, we had 10 tasks, so the user would put 10 here. Then the structure would take the array of the struct and then put it in a given size. Self-explanatory. Then secondly, this would basically, it's a for loop to insert all the values associated with each item of the array, each item slash task. So they would enter the start time, they would enter the finish time, the payment, as well as this is just an output message for the user. It would display all the, it will, it would display all the, uh, it would display all the information in one line so that the user can just review it at a glance. So it says it will show April, this to this, and then the payment, and then yeah. Now, as part of the algorithm mentions, you'd have to sort the array in terms of their finishing times. So this bubble sort basically helps me do that. It's, as you can see, it just sorts the finish time, as well as it outputs the first order, which is the most productive one. Then it would select task 1 for the sorted list, and then it would go through step 5 of the algorithm, which is it would iterate the loop over and over for each item to account for their finish time. So here, like the algorithm says, if the start is greater than or equal to finish time, then it would output it, as well as it's added to the payment value. After it has displayed, therefore, the program will display the order of which one is the most productive output time from here, as well as the maximum payment earned from here. All right, on to the knapsack problem. So the knapsack problem is similar to the activity scheduler problems in terms of coding implementation. First of all, I would have them insert the number of the size, but as well as the max weight limit that they're allowed to carry. And yeah, it would create a structure as well as a for loop to insert all the items one by one. So it would insert the weight for each items and the profit for each items, and then again it'll just display a solid line of information just so the user can skim read it and then figure out whether it's the correct amount. It's the correct information shown basically. Yeah, same like before, but now we have to sort the array in terms of their values, right? Oh yes, I forgot to mention the item I.value. This is basically calculating the value ratio of the program, which is the profit divided by weight. Then that's going to be used to sort basically the value ratio in terms of from highest to lowest. This is what the bubble sort again is for. And then this is the part where it would output the order of items that is most beneficial. That is that will lead to the maximum efficiency output. This is similar. This is like the similar. This is similar to the step shown in the algorithm. So first of all, it's a for loop, so it goes through all the items one by one, and then it will figure out that if the items if the weight of the items is greater than the max, and then it would add into it, as well as the profit. See, weight adds into the weight, and then the max profit add to the profit, and then it will keep going to the next one. Now, this is where the fractional method comes in. So the fractional method has to account for when the program, uh, when an item does not necessarily reach the maximum capacity of the weight limit. So this is what this is for. As you can see, it follows the algorithm. It will basically deduce the max minus weight multiplied by the value ratio of that item, and then account for it to the max profit. Yeah. Then the max profit earned will be basically it'll output the max profit. This is the multiply. I multiplied each of these by 1,000 because when I'm inserting the data, for example, 240,000, I'd rather write 240 and then have the program just multiply it by 1,000 to show the appropriate amount. I believe this saves the user time and then like potential errors because they'd have to select multiple zeros and all that. So now that the program has been explained, I will go ahead and run the code. Hopefully it'll work, please. And take some time. All right, so am I recording? Yes, I am. All right, so here's the beginning screen. Basically, it's asking, "Welcome." Yeah, it's saying my name as well as the main menu. Then it gives the user the choice to choose activity scheduler or knapsack. So let's go ahead and choose activity scheduler for now. So enter the number of tasks. The the example that we were given was 10 tasks, so I'm going to put 10, and then the start time for task 1 is 20, 23. The output is 240. All right. So this is what it means by what I mean by the singular message. It'll show task 1, which is correct, on April 20 till 23rd with payment of 240,000. It converted the 240 into 240,000. So yeah, let me just fast forward to inserting all the data. 26, 30, all right. So as you can see, it has worked successfully. It has says that the most productive task order is from task 1, moving on to task 6 and task 3 and then task 7. Then it will output the maximum payment earned, which as you can see is 1,530,000, and then it will finally ask the user to go back to whether they want to go back to the main menu or not. I forgot to slash end that part, but yeah. So let me just show you the next part. If I press Y, as you can see, it takes the user back to the main menu screen in which they could launch Knapsack now. Alright, so I had to cut the video just because I was editing the code to better fit our scenario, which was the Elon Musk Tesla wattage utilization problem scenario. Now that the output comments reflect the scenario, I feel like it's better visualization. And other than that, the code has remained the same. Nothing of its function has actually changed that much. So let's go ahead and insert 2 for knapsack. It'll ask us for the number of components. We could type 7. Now it'll ask us for the total wattage limit, which is from the example 20. Alright, so it asks us for the wattage component. That'll be 2. And then the utilization value is 45. Now it shows the user a one-line message just so that they could make sure everything is correct. Now let me go ahead and insert each one. All right, so here's the last value, which is 42. Boom. Okay, so you can see that the program has functioned successfully. It says, it gives us the order of items that's supposed to be component, the order of the components that is most the order of components that is most efficient, as well as their maximum utilization efficiency. So yeah, the user can either to go back to the main menu or not. Since we've already demonstrated that they could go back to the main menu, we can go ahead and press no, and the program would successfully close itself. All right, so the law firm has shown us this set of data for us to use, as well as his request. He's a lead partner in a lawyering firm who has been losing potential clients due to the mismanagement in scheduling. He requires an algorithm to find the most efficient way to meet the most of his clients in a given day in order to maximize productivity and minimize financial costs. Looking at this problem at first hand, you can see that it has a start time, finish time, as well as the consultation fee, aka payment. These are the consultation, which we will bracket task. Therefore, we can assume that the optimal solution would be to create an algorithm, to create a program for the activity scheduling problem. And this is client B, aka Elon Musk. Elon Musk has his description here. He is the CEO of a large electric vehicles company, Tesla, and he wants his new Tesla Roadster models to run at peak efficiency by maximizing the utilization of car components from a fixed battery wattage. He has given us this set of data. Car components is in brackets items, so I1 through I7, as well as their utilization value, their wattage throughput, and the total wattage limit, which is 20 kilowatts per hour. Now, from face value, we can therefore conclude that the optimal solution would indeed to be to use the knapsack problem. Thank you for watching my presentation. I hope my presentation was informative, it was detailed, it was coherent, as well as entertaining. Assalamualaikum warahmatullahi wabarakatuh.